Hi, and welcome back to another supervised learning video. Last time we introduced the exponential family of probability distributions. In this video we're going to develop the ideas of a generalized linear model and motivate the idea of a link function. In previous weeks we've already met the linear regression model, in which we considered our responses yi, for I is 1 to n, as independent Gaussian random variables, where the variance of those random variables is constant across responses, but the mean of each response, mu I, is allowed to change as a linear combination of some row vector of covariates, which we call xi dot, and a column vector of regression coefficients, which we call beta. We've also met logistic regression, in which our responses are considered as Bernoulli random variables, and the probability of a so-called successful outcome is allowed to vary between each observation. We can consider this variation either as the log odds of a success being linear in the covariates, or equivalently as the probability of a success being the logistic function of that linear combination. In each of these cases, we're modelling our outcomes using an explicit probability model and describing the model parameters as potentially functions of a linear combination of predictor variables. Generalized linear models, or GLMs, extend this idea to give us a unified framework in which to model outcomes from any distribution in the exponential family. In fact, since both the Bernoulli and the Gaussian distributions are within the exponential family, linear and logistic regression are both special cases of GLMs, and we're familiar with at least two GLMs already. In a generalized linear model, we consider our responses to be independent realizations from a distribution within the exponential family, which either has one or more parameters that we refer to here using the vector theta. We're going to let one or more of these model parameters vary between responses according to some function h of the linear predictor corresponding to that response. You should note here that if we have multiple parameters depending on the predictor variables, then h will be a vector-valued function. You can use exactly the same modelling approach for distributions that aren't in the exponential family here, but while that's still in the spirit of a GLM and a useful modelling approach, you have to be cautious because much of the well-developed theory around GLMs may or may not be valid in that case. What we have is in the spirit of a GLM, but it's formally not a GLM. So generalized linear models give us an explicit and tractable stochastic model for our responses given our predictor variables. This allows us to construct a likelihood function, a log likelihood function, point estimates and confidence intervals in much the same way that we have been doing for linear and logistic regression models already. In the next video, we'll see a particularly efficient way of obtaining the maximum likelihood estimate for our regression coefficients. We'll come back to discuss some additional considerations about this modelling framework after we've considered a tangible example, but for now you know the core idea of generalised linear modelling, and I hope you'll agree it's not as complicated as it sounded at first. Suppose then that we have some data from a cloth manufacturer. We've been given some information on the lengths of some reams of cloth and the number of defects on each ream. Clearly we've got an increasing and potentially linear relationship here, so we might be tempted to use a linear regression model. However, the defect counts only take integer values, and it appears as though the variance of the defect count is increasing with cloth length. Both of these are violations of our linear model assumptions. So instead, we might use a GLM to model our defect counts as being Poisson distributed, where the mean defect count lambda varies as a function of cloth length. To ensure that our expected number of defects is always going to be positive, we have to choose our function h judiciously. One option is to take h equal to the log function. This is known as the canonical link function, since it's equivalent to modelling our canonical parameter that we found in the previous video to be mu equal log lambda as a linear function of the covariates. As in a linear regression, it's going to be prudent here to centre the lengths of each cloth around their mean value to reduce the correlation between the estimates beta 0 hat and beta 1 hat. If we were to fit such a model to our data, and we'll cover more on how to do this next time, we'd then have parameter estimates beta hat 0 and beta hat 1, and estimates of their uncertainty. We could then leverage the invariance property of the MLE to estimate the number of defects in the ith cloth as the exponential of beta 0 hat at beta 1 hat times the difference to the mean cloth length of the ith cloth. This gives us a point estimate, and to construct confidence intervals for each of the lambda i's, we can use either the delta method or Monte Carlo simulation. Under this fitted model, we can interpret the exponential of beta 0 hat as the expected number of defects in a cloth that is of average length, and the exponential of beta 1 hat as a factor by which this is going to change for every additional meter of cloth. As with a linear or a logistic regression, we're not limited to using a single predictor here, or even to that predictor being real valued. For example, we might have two cloth types, cotton and felt, and a second predictor, which we'll call x.2, which is a dummy variable indicating that the cloth is felt. We could then fit the following Poisson regression model, as given on the slide, and this is a generalized linear model in which we're allowing both the expected number of defects in an average length of cloth and the multiplicative effect of cloth length on defect count to differ between the two cloth types. This type of model would allow us to formally test whether an average length of cotton and an average length of felt have the same number of defects, or if the number of faults increases more rapidly with cloth length in cotton than it does in felt. You'll see a lot more about answering this sort of question and performing model selection in the next week's videos. So finally, let's return from our particular Poisson regression example to our general formulation of a GLM. What exactly should we be considering when we're selecting a particular link function h? Well, this is going to depend on the modelling context and on the support for the model parameter or parameters that we're linking to our linear predictor. Ideally, we'd like a link function that is sensible in context, that allows for relatively easy interpretation of the regression coefficients, and ensures the parameter value will be permissible whatever the values for the predictors. Often we'll end up choosing the canonical link functions, those which express the parameters in terms of the moments of the response, for example its mean. These canonical link functions usually give our model nice statistical properties and an easy interpretation, but what they might not do is a good job of representing the true relationships between the response distribution and the predictive variables themselves. We've seen an example of this already with Bernoulli regression, where, among others, we have the option of logistic or probit regression. Using the logit link function often leads to a tractable and interpretable model, but sometimes using the inverse of the normal CDF, phi inverse, or some other link function instead, is going to allow for a more efficient inference process or better capture the underlying relationship between predictors and the response distribution. So in summary then, in this video we've defined the class of generalized linear models. We've considered Poisson regression as a special case and how we can interpret a fitted Poisson regression model. And we've also considered the points that have to be balanced when selecting a particular link function h. In the next video, we're going to look at how to estimate the regression coefficients beta themselves within a GLM by maximum likelihood through an algorithm known as iteratively reweighted least squares. Thank you again for your time, and I look forward to seeing you in the next video.